This is the last unit, or last slides for Unit 1, 2D kinematics. And it covers gravity and the acceleration due to gravity. So we know gravity is a thing. It's not something new. Acceleration due to gravity is approximately 9.80. This class we tend to use 9.81 for gravity. There are even some problems where you'll see that it is, say, use as this. And so use as 10. And that just, and when we say use acceleration due to gravity at 10, that just makes our lives a lot easier when it comes to math. Which you're not too far off. And if you ever need it in like a real world, kind of like, well, how far is something when I drop it? That works out real nice by just kind of using 10. It does have a symbol of a lowercase g. Okay. All objects fall at this rate. And so that's kind of the, you know, how fast is it falling? Well, it's always going to fall at gravity's rate. The rate in which gravity falls. Or all objects fall at that. Now, at some point, an object will reach what's called its terminal velocity. That terminal velocity is the fastest that the object will ever go. It's still accelerating, it's just at a constant acceleration. And the velocity is also going to look like it's increasing, but it's going to just kind of plateau out. How long it takes, at what point, and and what is the terminal velocity for each object is different. Graphically, what does it look like? Well, because an object is accelerating, that means our speed or velocity time graph needs to look like it's a direct proportionality, that nice straight line. Our distance time graphs need to look as if they are quadratic, because they have a curvature to them. One of the beginnings of okay, what is the slope of this line? Well, it's constant, but it needs to have a curvature for the distance time, because that's the tell that something is accelerating. If there's a curve to the graph. A speed time or a velocity time graph, the tell that an object is accelerating is a straight line. Kind of like, okay, what would the slope of this line be? It would be a straight line moving in the positive direction. Okay, what would the slope of this line be? Well, a slope of a speed or time graph should always only be a straight line. And when an object is falling, it is always falling at a constant acceleration. So the constant acceleration equations do come into play. Now, we can all actually factor out some things in those, and that actually gives us new equations for gravity specifically, even though they are derivatives of the actual equations from constant velocity that we have. And you'll look at it and you'll recognize them when we see what's going on. So the instantaneous speed of an object falling is going to be based on the time. The final velocity is equal to gravity times time. This is also taking into account that you don't know the initial. If you do know the initial of, say, an object was thrown downwards at the initial velocity, then you have to use one of the constant acceleration equations. But this one is an object is dropped due to gravity and falls due to gravity. What is it right before it hits the ground? Kind of a thing. Many times using the distances, where distance or x, and that in all reality, that should be that should not be x. It should be y, shouldn't it? If we're dealing with gravity, because gravity is in the y direction. Maybe a d sub y. And that's 1/2 gt squared, which should look very similar to the x is equal to v sub I times t plus 1/2 gt squared. In this case, why you're using that one? Well, the initial velocity, if you drop it, it's going to be 0. If you throw an object up in the air, at one point at the top of its apex, the velocity is going to be also 0. And so sometimes we use that as a means. As it went up so high in the air, how much time did it take for it to fall? So then you have to kind of roundabout go around different things, find the hang time, but you have to multiply it by 2. If you only take into account the time that it takes to drop, you also forgot the time that it takes to go up. So you got to be careful about some of those things. But it is what it is. What would the speedometer read of a falling rock at 4.5 seconds after it drops from rest? From rest. And because I tend to use 9.81, and that comes from we used to, when we had mastering physics, it used 9.81 all the time, so we just got used to, just got used to doing that. It's like 15.99 for oxygen, even though it should be 16 rounded up, whatever it may be. Okay. We have time at 4.5 seconds. This one's nice and straightforward. Gravity times time. (9.81 meters per second squad). 4.5 seconds. that into my handy dandy calculator. Get a velocity of 4.1. Yeah, well, you go 4.11 decimal on that, even though there's supposed to only be 245. Then, yeah, so meters per second. What would it be after 8 seconds? Well, not much different. Just some numbers are going to change. So one thing that's nice about gravity, it doesn't change much. Stays pretty constant. So it does allow for that. Does that answer even make sense more frequently? And so we can look at our answers and go, you know, somebody might look at it and say 78 meters per second or 78.5 meters per second. Does that even make sense? Yeah, if it's falling for a long enough time. Taking out of the fact that, you know, aerodynamics could maybe slow it down a little bit, but maybe it's not. 78. Oh, gosh. 25 meters per second is about 55 miles an hour. It's moving.
This is also only a theoretical rock.
Yeah. So, let's see what happens. An apple drops from a tree and hits the ground in 1 second. What is the speed upon striking the ground? What is the average speed during that 1 second? How high above the ground was the apple when it first dropped? That is a lovely loaded question.
But would we have to know one of the answers to get to the other?
Yes, we do have to know more than what. We have to kind of solve some of these to solve it all. You have to solve 1 and 2 to get another opened up.
Or couldn't there also be
So I'll resize this a little bit because we're going to have a lot going on. Okay, so maybe I'll draw a little tree here. Okay. The time it took for the object to fall would be 1 second. Gravity is going to equal 9.81. We want to know V sub f. We also want to know average velocity or speed. We also need to know how high it fell. Well, the first kind of solve that we need, or can be solved for, the V sub f, that should be pretty easy because it's 1 and 9.81 meters per second squared times time will give us 9.81 meters per second. Now, an object that is falling is going to be d sub y, or just y, 1/2 g t squared. Well, this one also isn't too terrible, because 1 squared should be just 1. So then 1 times 9.81 is 9.81. 9.81 divided by 2. It's actually probably going to be a number that you are going to almost know off the top of your head at some point in time. And that's 4.905 meters. So how would I find the average velocity or the average speed? Average, remember, is total distance divided by the total time. Which then is just the 4.905. Some people will ask, why is that half of it? Well, the object has to speed up as it falls. It's not going to just instantaneously be moving at 9.81 meters per second. It's going to fall at 9.81 meters per second squared, but it's got to move into that speed. Is the object rolling down a ramp the same at the fastest at the top, middle, or bottom? It's fastest at the bottom. It is going to be the fastest right before it hits the ground. The last one to leave you with. So you have you and your friend stand on the edge of a 40-meter cliff. You throw a red ball straight up at 30 meters per second. At the same time, your friend throws a blue ball straight down at the same speed. Compare the velocities of the two balls right before they hit the ground. How much later does the red ball hit than the blue ball? Sometimes it's going to be very helpful to make sure that we draw out what we have here. And so when we're going to resize this, and we're going to redraw this scenario. So we'll have our cliff here. We are going to have a red ball straight up. Now normally the red vector will be velocity, but we're going to keep the velocities in the color of the object so that we can see what is going on. The distance of the cliff to the bottom is 40 meters. Now the blue ball gets thrown down at 30 meters per second as well. Compare the velocities right before they hit the ground. So we want to know v sub f and v sub f. We also want to know the time that it is different for the blue ball to the red ball hitting. This is going to take us and think about some things, because there are some things that's going to happen. The red ball is going to go up, and it's going to be at a point before it comes down. And so that's going to factor in the time. So we have to figure out how much time, and we're going to we can go and infer that the object isn't going too much left or right, that's all variable. And so we have some things that we will also have for us as well, and that we have initial velocities. We have a distance. We have what we're solving for is the final velocity. We might not be able to use the equations that we had earlier of v sub f is equal to at, because we don't have time. We might not be able to do the distance is equal to 1/2 g t squared, because we don't have time. But remember that the acceleration is constant, and therefore the acceleration of gravity, 9.81 actually, negative 9.181 meters per second squared, we can use any of the equations that have a constant acceleration. So we really need to find is what equations do we use to solve for that. So let's solve for the red sphere first. So I'll write most of this in red. Because I know at the top of this, that v sub f at that time is actually going to equal 0, which is actually very important information. That's going to actually tell me how much distance the object went up. So that one, I can use the v sub f squared is equal to v sub I squared plus 2a, and then the change in displacement, and in this case, it'd be d sub yi, or d sub y. And I'm going to just say 1, because the other 40 is going to be added to it. Because it's also going to go up, and then it's also going to come down. So it's actually going to be falling. And that's really what we want to know, is how long is it going to be falling, because then we can solve for some other information that we can use. We're going to have 0 squared is equal to 30 squared plus 2 times a negative 9.81. Solving for the delta dyi or dy1. Okay, and then we have, put that into my handy dandy calculator on your 30 squared minus, because negative 9.81, 2 times 9.81. Oop, almost got mixed up there. Is going to give me 19.62. Then would move that over, so I'd have a negative 900 is equal to a negative 19.62 d1. Solve for that, which means I need to take my 900 divided by 19.62. The negatives would cancel out to give me a distance 1 of 45.87 meters vertically. Okay, that's how far it goes up. Now, it's also going to be coming down. So its actual total distance traveled is going to be 45 plus the 40 that it went from the cliff. Therefore, we should be able to figure that out now. But here's the thing. The distance that it's traveling, and once they actually get to the same height, they're going to fall and should fall that same amount of time. But remember, the blue is going down first. The red has to go up, then down. We can solve for that time using the 1/2 GT squared. Solving for t. So you would end up having this divided by, I believe that is, what, be 4,905? Would be equal to the t squared. We'll need to take the square root of that. To give me a time of 3.06 seconds that it takes for it to go up. And then it's also, that would be the up time. And then we need to double that to get it for the total time, which would give us time of that of 6.12 seconds. Now, because we have an initial velocity going down and that, it should come at no surprise that the velocities, that's not going to really matter as much as we maybe initially once thought, is because we're not asking total. We are going to find, and eventually do need to find, the total time. Now, the time that it takes for it to fall 40 meters will be needed to take into account in the final velocity. The final velocity for the blue should not be less than 30 meters per second. So we need to make sure and evaluate our answers. And to take that into account, we can use the equation v sub f is equal to v sub I plus, not times, plus AT. Now remember, acceleration is just another fancy way of saying gravity. So we would then have 30 meters per second down, which would technically be negative, then plus 9.81 for that. Now, we have to solve for our t and our v sub f. Well, that's not very easy. So we need to take something into account, and we need to find, using our equation here, we need to find our time, the time that we originally needed to find. And so we can do that by plugging our time in. Our distance that it's in is equal to 1/2 gravity times time. And we should get that time that it has in for it. So we gotta take 40 and divide that by the 4.905 and take the square root of that. And we're going to get a pretty small answer of time of 2.81 or 2.86. So I put that in. It doesn't fit in very nicely. Point 8.6. Multiply all that out. Plus my 30 to get that the final velocity is 58.01. Now, coincidentally, the velocity that the object had, the red ball had when it was thrown up, is also going to be 30 meters per second when it's coming down. In the negative, obviously, but it's going to have that same velocity. So they're both going to have the same velocity. They're just going to hit the ground at different times, and the time delay is the amount of time that it takes for the red ball to go up and then down before it actually falls all the way down onto the ground. And thus concludes the end of Unit 1 and in one-dimensional kinematics.